right? So these concepts were discussed in previous lectures, right, where we saw the basic circuit of an op-amp and what are the uh, parameters involved, or what are the components involved inside an op-amp circuit was discussed, right? So as you can see, there is a differential input stage, there is a level shifting stage, and there is a voltage follower output stage. Okay, so this is the basic circuit of an op-amp, right? So moving on, we had seen the types of inputs, right, that can be given to op-amp, right? So these were the types of inputs or the supply voltages that can be given. Now op-amp can either function in an inverting mode or non-inverting mode. Can someone tell me what's an inverting and non-inverting mode?
VCC is given to the negative.
Okay. VCC is given to negative, you're sure? No.
Inverting terminals.
Now what is inverting outputs and non-inverting outputs was my question. You mean to say the inverting terminal, the plus symbol here? Okay. Now, the thing that you should understand is whenever an input is given to minus, okay, which is an inverting terminal, then the output becomes inverted. If an input is given to the non-inverting terminal, that's the plus. Now remember, this plus and this plus VCC are totally different. Okay, so this VCC and VEE is actually needed to power up your op-amp, whereas these pins, pin number 3 and 2, is also given as plus and minus, but then it is not supply. Okay, these are input voltages. Okay, these are input signals that are given to terminals 3 and 2. So in 3, if the supply or if the voltages are given, then it becomes non-inverting, and if it's given to 2, then it becomes inverting. So is it clear the difference between this plus here and the plus VCC here? Yes?
Yes.
Yeah. So do not get confused with both of these plus. Okay, this plus and minus is actually needed to power up your op-amp. Okay, which is needed to turn on your op-amp. And this plus and minus is the inverting and non-inverting terminal of the op-amp, which accepts the input signals. Okay, so do not get confusion. So we had seen these three configurations with the op-amp, right? The first one was voltage follower with directly connected signal source. So we call it voltage follower because whatever is the input, okay, the same thing comes across your output. So we call this as voltage follower with directly connected signal source. So we have a signal source here. And the second configuration that we saw was we can have a coupling capacitor provided we have a resistor. So if we have a resistor here, then we need to have a CC, which is coupling capacitor. And the output is directly taken across the load RL, here also across the load RL. Now if in case I just want to use plus VCC and I want to ground the other terminal, then I will have to use voltage divider here. Okay, so this voltage divider will make sure that my voltages are exactly divided by 2 Okay, I have given an example here where if plus 30 can be used instead of plus or minus 15. So instead of giving plus 15 minus 15 here, I can just give plus 30. So with the help of these resistors, the voltage is going to get divided. Okay. So this was one of the configurations that we saw. And here, since we have a voltage divider, okay, there are two resistors here. So I'm using another capacitor at the output side, which is called the coupling capacitor. Sometimes this capacitor is also called coupling load coupling capacitor. So which means this coupling capacitor is actually present with respect to RL, okay, with or together with RL. Is that clear, students?
Yes, sir.
Fine. Now moving on with the next concept. Okay, yeah, supply voltages. Now we will move on to something called input voltage range. I want all of you to concentrate here, okay, because these concepts are very much important to understand, because questions can be asked based on these. Okay, the question can be, with a circuit diagram, explain the input voltage range of an op amp. Okay, or it can be explain the output voltage range of an op amp, right? Okay, so this is our circuitry, okay, where we have Q1 and Q2 transistors, and we have the resistance RE, and we are giving one input here to Q1 and to Q2 another input. So these inputs are V1 and V2, and accordingly these currents are generated, which is IC2 with respect to Q2 and IC1 for Q1, right? Okay, the voltage across the resistance, okay, RC is called VRC, and the voltage across my Q2 is called V2 with respect to ground. So one terminal I connect here and the other one I connect to ground. I get to know the voltage which is actually across my V2, or this can be our input, right? Because we know how much input that we are giving. So this is my V2, this is my VI. Fine. So we have plus VCC and minus VEE, and this output voltage is taken across the resistor RE3, which means the resistor which is across emitter and the third transistor. Okay, Q1, Q2, Q3, T1, T2, T3, transistor 1, transistor 2, transistor 3. Q3 is your operating point. Okay, fine. And this RA and RB, this forms a voltage divider, right, as we have seen previously. So I think now the circuit is clear for all of us as to how this is analyzed. Okay, so as the input voltage is increased, now I know that if in case I give minus 5 here, okay, minus 5 is given here, and the other transistor tries to become plus 5, right? So the reverse process is also true. If I give minus 5 here, okay, if I give minus 5 here, this, the other transistor Q2 will try to upscale its voltages, its potential difference to the same as the input, but with the reverse polarity. So I think this concept is clear with all of you. Is it? Yes? Okay. As the input voltage is increased positively, okay, so let us take first case. Let us take case by case. Case number 1, where let us say I'm having a positive voltage here. Okay. As the input voltage is increased positively, the output follows it. Okay. So since the input voltage is increasing in a positive way, this output will actually follow whatever is there in the input. Okay. So that's why this is called voltage follower circuit. Right? Now, since this increases positively, okay, so what happens to Q2? This should reduce negatively. So in order to get this reduced negatively, my IC2, okay, will also get reduced. The current will get reduced, whereby the current in IC1 will get increased. Is it clear till this point?
Yes,
Yes,
sir.
Fine. Okay. Now, why is this happening? Because this is a differential amplifier configuration. Okay, so the motive of differential amplifier is it wants to nullify, or it wants to make the output voltage zero, right? So that is why, to balance out, if IC1 increases, then IC2 decreases. Okay. Now, till which point can it decrease? There are certain regions of operation for a transistor: cutoff, linear, and saturation. Can someone tell me what is cutoff region for a transistor? I think you would have studied this in your analog electronic circuits course. What is this cutoff region of operation?
a region that transistor acts as an amplifier.
Will it be functioning at that point of time, cutoff point?
Sorry, as a switch.
Yeah. So there is a limit to which we can reduce or increase the voltage level. So if I just keep on increasing this voltage level and make it more positive, it can only reach to a point called cutoff, after which even though these levels are increasing, okay, even though these levels are increased to a higher level, this cannot come down, okay, because it's already down, right? It's already reached a level, so it cannot go beyond that level. So which means even if you increase more positive, even if the input is given more positive, there is a limit at which this currents can reduce, right? So which means at some point IC2 is so small that Q2 approaches cutoff. Okay. So Q2 is approaching cutoff. So what is this cutoff? Cutoff, as I mentioned, okay, is going to be, okay, so this is important. Yes, IC2 is so small that Q2 approaches cutoff. So it reaches cutoff, which means the minimum voltages are actually, minimum currents are actually in Q2. So it cannot go beyond that. It cannot become more less than that, is what I'm trying to say, right? Further increasing Vi has no effect on the circuit. Now this is important, right? It has no effect on the circuit, even though it is increased in a positive fashion. Okay. Even though this goes higher and higher and higher, okay, but still this cannot go still lower, okay, because it has already reached its cutoff, which means it is in off state. So at this point of time, we can say that it has reached its maximum positive going limit. Okay, so if in case I draw waveform, okay, and if I call this my axis, okay, now I can say that this is my maximum positive point, correct, and this is my maximum negative point, isn't it? Do you all agree with this?
Yes.
Yeah. So it cannot go beyond this, right? And it cannot go below this point. So that is what we are trying to see here. So at this point, we see that it has reached its maximum positive going limit, which means it has reached its maximum positive cycle. Okay. Now we have learned with the first case, which is the positive cycle. Now we have to look into the reverse process, which is the negative cycle. So in negative cycle, what happens? The reverse process is also true when the input is increased in a negative direction. Now we are coming in the opposite way. Instead of increasing, okay, what will I do? Now I will try to decrease it. Okay, I will try to decrease this point as much as possible. And what happens when I decrease this? My IC1, will it increase or decrease?
It will decrease, sir.
Very true. So it will decrease.
Increase.
It will decrease because my voltage is decreasing, my current will decrease. Right? And what happens to IC2 with respect to
It
the
will
second
decrease, sir.
transistor? Yes, because one is
Increase.
decreasing, the other one
Another
will increase. Okay, so it is like a seesaw. Remember, these two, Q1 and Q2, is like a seesaw. If one goes high, the other goes low. If the other one is low, the other one goes high. Okay? So it's just that concept. Okay, fine. In the negative direction, IC2 increases to increase VRC in order to drive VB2 down to keep the output following the input. So output is made sure that it is following whatever output that I'm getting here should be equal to whatever input was given. Okay. So in this case, as we saw, my IC1, what is it happening? IC1 decreases in order to increase IC2. That is true, right? And the next one that we're going to see is the limit of the increase in IC2 occurs when Q1 approaches cutoff. So now previously, which was in cutoff in the previous case, which was going into cutoff? Was it Q1 or Q2?
Q2, sir.
Exactly. Now Q1 will go into cutoff region and Q2 will be in its maximum operating point. Okay. So when Q1 goes into cutoff, we can say that V high has arrived its negative limit. So this is what I'm talking about. Okay, so this region is what I'm talking about. So it has reached its maximum negative limit. So have you all understood this concept?
Yes, sir.
Yeah. Okay.
Yeah,
So
sir.
ultimately, you should understand that this transistor or the differential amplifier works like a seesaw. Okay? It makes sure that if one level at one point is low, the level at the other transistor increases. Okay, this is made to make sure that the output is driven, okay, based on the changes in input. Okay, so if everything is fine, then we'll move on to the next concept. Can we move on?
Yes, sir.
Okay. So the next thing that we'll be looking into is the input voltage range. I think many of you would have seen these characteristics, right? The maximum voltage that it can take, maximum positive voltage that it can take, the maximum negative voltage that it can take, right? So all these are called ranges. Okay. So if you can see the input voltage range, okay, the minimum that it can go to is about plus or minus 12 volts. If in case I am giving the supply as 15 volts, keep in mind, if in case the supply is how much? 15 volts. So typically it will maintain about 13 volts. So plus VCC, which means plus 13 VCC minus 13 VEE is maintained, and it can go down to about 12 volts. Okay. And you can see that the output voltage swing. Okay, what is the swing? The maximum levels that it can reach, the output voltages that it can reach. Remember, I had drawn a waveform, right? So the maximum that it can reach is called a swing. Okay. So you can see here that it is about 10 kilo ohms, and the typical range is about 14 volts to 12 volts. Keeping in mind that the room temperature is about 25 degrees centigrade. Are you all aware that the circuits perform differently with different temperatures? Yes?
Yes.
Yeah. So every degree rise in temperature will actually impact the voltages. Okay. So if say if I'm taking this 25 degrees centigrade as the standard, and probably I operate at 26 degrees centigrade, then the output voltage that I'm going to expect is going to be completely different as that of 25 degrees centigrade. So approximately, there is going to be about 10 millivolts range of difference. Okay, right. So the maximum effective positive going and negative going voltage that may be applied to input of an op-amp is termed as input voltage range. So this can be asked in your tests as to what is meant by input voltage range. The maximum effective positive going and negative going voltage that may be applied to an input of an op-amp is called input voltage range. So ultimately we are looking at ranges that helps us in understanding as to what is the maximum and what is the minimum, right? Okay. So similarly, you have other things here, which is supply voltage rejection ratio, common CMRR, common mode rejection ratio, what is the minimum, what is typical, and what are its units. Okay. Now, these are some points that I want you all to look into. Okay. With the voltage follower discussed, see, we had discussed this concept, okay, which is nothing but voltage follower. Okay, so keeping this in mind, okay, keeping this circuit in mind, we will be understanding what is output voltage range. We see that the output is limited by the input voltage range. Do you all agree with that? Is the output limited based on the input?
Yes, sir.
Yes. How is it so? How is it so? Can someone explain as to what we have discussed so far? How is it so? When the transistor reaches its cutoff state, okay, even though you make V1 more positive, okay, there's not going to be any effect on Q2, which means your IC2, the current with respect to the collector of transistor 2 has already become very low. Okay, so it cannot go beyond that. So in order to see that, okay, in order to get the balance between them, okay, so this is happening. So ultimately our output is also limited based on our input. The next one, when op-amp is connected to function generator, okay, it can be either in inverting or non-inverting configuration. I can say inverting when the signal is given to the minus of the input, right? And I can say non-inverting when the signal is given to the plus. Okay, the 3 and 2 that you see. Yeah. So the output voltage is likely to be much larger than the input. So what is the gain of op-amp? How much is it? Does it have very high gain or very low gain? Yeah, students? Op-amps do have much higher gain. Okay, so that's why you can see that the output voltage is also much larger. Okay, when you connect it stage by stage. Okay, the output voltage can swing in positive or negative direction depending on the supply voltage and on the op-amp internal circuit. Now, what do we understand by this? Based on how much of input that I am giving, okay, my output can go to positive direction or negative direction. Okay, so we have seen in the operation in the previous slide, right? The specifications mentioned in the previous figure, okay, is actually referring to resistors not less than how much? 10 kilo ohms. Okay, so if I'm using resistors less than 10 kilo ohms, and whatever specifications that I have given there, okay, which is about 14 volts, 13 volts, all that will tend to change, right? So which means resistors play a very important role when we are deciding on what kind of circuit that I need, how much of output is needed, how much of input voltages that I am giving, and in which stage that I am going to connect this circuit. Okay. Now, an important concept that you will have to note down is with low resistance loads, the output voltage range is reduced. Okay. So if I'm having lower resistance, okay, so which means there is much probability of the currents to flow in, the output voltage range is reduced. Okay, so I don't have to really give a large range because the resistance are too low, right? So with less potential difference, I can achieve my output. Some op-amps have an output swing that extends from minus VEE to plus VCC. The range that we saw, right? So it can vary from minus VEE to plus VCC. Now this is called a rail-to-rail operation. Okay. Rail-to-rail operation. You should be remembering this. A question can be asked, what is meant by a rail-to-rail operation? So if you find op-amps whose outputs are swinging between the ranges minus VEE to plus VCC, this is called rail-to-rail operation, which means it is going from edge to edge. Okay, let's say plus VCC is about 5 and minus VE is about minus 5. Okay? So if your waveform is touching, okay, plus and the minus levels, okay, the plus and the minus levels, then we can say that it is a rail-to-rail operation. Many times what will happen is if I check this value, okay, if I check this value, it may not be exactly about minus 5, okay, but then it could be about probably say 4.5, okay, minus 4.5, okay. So in that case, can I call it a rail-to-rail operation? Yes, can I call it rail-to-rail operation? and the supply is -5 plus or -5? Yes, students, I want you to answer. We cannot, right? So we can call it rail to rail operation only when it is having -5 to +5. Okay, the full input voltage, whatever is given, if I can observe it here, okay, then I can call it as rail to rail operation. So are we clear with these concepts that we have discussed so far? Yes.
Yes.
Okay, fine. So we had seen this output voltage range, right? That is necessary for understanding the swing, right? And if in case it is going from +5 to -5, which means, I mean to say, the maximum, then we call it as rail to rail operation, right? Okay. So moving on, we will just probably look into one example. Okay. So this was a circuit that I had told you all to draw, right? And meanwhile, you can just take down the values. So this is going to be our reference circuit, okay, on which we are going to solve the problem. So which circuit is this? Yeah, which circuit is it? You're all able to hear me, right?
Yes.
Yeah, so which circuit is it? So this is nothing but the basic circuit of your op-amp. Remember, I had told you that we have three stages: differential input stage, the level shifting stage, which has the uh, resistors, which acts as voltage divider, right? And then we have the last transistor, okay, Q3, which is the voltage follower output stage, right? So just make note of the values and let me know once you're done. Okay, so here we are asked to calculate the voltage and current levels for the circuit, okay, which is given here. And as I mentioned previously, this is our basic op-amp circuit, right? Okay. Right. So here we are seeing VCC is given about 10 volts and V1, V2, okay, is equal to 0. The components are RA, okay, the one that you see here, RA is about 47 kilo ohms and RB is 100. If possible, what you can do is on the circuit only, you can just small, in short, you can write, okay, in small font so that you will understand. And RC, RE, and RE3. So this RC, okay, and this RE3, okay, and RE. So 1, 2, 3. So these three resistors are about 4.7 kilo ohms. For simplicity, assume that Q1 and Q2 are perfectly matched. So which means that they are acting as a perfect match, a replica of each device. Okay. Now one thing you should keep in mind, even though a transistor is manufactured by the same manufacturer, the same batch, no two transistors can give you the same outputs. Okay. So what I mean to say here is, let us say in year 2021, let's say batch 1, okay, batch 1 of transistors are manufactured. So in batch 1, I will have transistor 1 and transistor 2. So even though it is manufactured by the same manufacturer in the same year, the same batch, but these two transistors, which is T1 and T2, will not have the same properties, right? But here we are assuming that Q1 and Q2 do have similar properties. So Q1 and Q2 are perfectly matched, that the current through RA and RB has no effect on voltage drop. So whatever current that is passing through RA and RB has no effect, okay, on the voltage drop across RC, and that Q3 base current has no effect on the voltage divider, and Q3 has no effect on the voltage divider. So assuming that there is no reverse current flowing through. Fine. So how do we solve this? We have to take it step by step, right? So first, we will find out what is VRE. So as you all know, okay, you've all studied network analysis, isn't it? So based on those concepts, okay, VRE, okay, which means the voltage across the resistance RE. So this voltage across the resistance RE is nothing but VB1, okay. VB1 is for the first transistor, the voltage across base 1 minus VBE minus VEE, because this terminal is here, right? So this terminal is here, so minus VEE and minus VB1 and minus VBE. Okay. So if I put those values, it becomes 0. Remember, we have given 0 and VBE is 0.7, so because it's silicon, then VEE is minus 10 volts. So if I calculate, my VRE is going to be 9.2. So once I get this, the next thing is to find out the current across resistance RE. So how do I get current? V is equal to IR. So I know what is VRE, I know what is the value of RE. So it is simple for me to calculate the current. So IE gives me about 1.98 milliamps. And we know that IC1, IC2 is equal to, it is perfectly matched. So it is going to be half of whatever current that is coming through here, right? Because it's a branch. So IE divided by 2, so which means it is approximately say 2 milliamps here, so it's going to be about 1 milliamp. Okay, right. Next, VRC. Okay, VRC. Now I'm going to find out the voltage across RC. Okay, VRC. VRC is equal to IC2, V is equal to I into R, I into RC. I know the value of IC2 because IC1 and IC2 are equal to D by 2, which is 0.99, right, into RC. So RC is 4.7, right? So when I multiply them, then I'm going to get about 4.65 volts. Next, the voltage across RA and RB, okay, is going to be nothing but VCC. Why? Because these two are connected. Okay, these two are connected. Now, one of the terminals are connected to VCC, and the other terminal is connected to minus VEE. So this, the total voltage across them is going to be VCC minus VEE minus VRC. The same thing is here because we have already calculated this, right? So this becomes, it says that, in the question, if you can read, it says that RB does not have any effect. Okay, so which means it's going to be as good as VRC. Okay, so 10, okay, because it has plus or minus 10, so 10 minus of 10 minus VRC we have calculated here, which is 4.65. So when I calculate, I get about 15.35. Okay, so now individually I will find out VRB, okay, based on my parallel concept. Okay, so VRB is the total voltage, okay, the total voltage VRARB, okay, from this point to this point. Okay, so that is my total voltage into RB divided by RA, the total resistance RA plus RB. Okay, so when I substitute those values, okay, so RARB is here, and my RB value, we know that it is 100 kilo ohms, right, divided by 100 plus, and RA is also known to us, which is about 4.7. So I find out that my value is going to be about 10.4, 10.5 volts. Now the output voltage is actually here, right? Output voltage is actually here, and one of the terminals are connected to VEE, right? And then we have voltage VRP, and then VBE. Okay, the voltage across the emitter region of Q3, right? So we make sure that VEA is minus 10, right? And VRB we just found out, which is about 10.4 volts, because this resistor is connected here, right? This is the loop. And VBE, right? VBE, the voltage between the base and emitter, is minus 0.7, right? So after this, I find out that my total output voltage is going to be about 0.3 volts. Okay. So this problem actually has all the concepts covered. Okay, right from finding out the voltage from this one, okay, which is nothing but your emitter resistance, and then the divider concept of currents, okay, equally getting divided by 2, and then finding out the values of VRB, and then finally taking the value of V0, right? So I hope this concept is clear for all of you, right? Any doubts, students?
Sir, why VB1 is 0?
Which one? VB1. Yeah, because in the question, right, we have taken V1, V2 is equal to 0, right? So that's the reason.
Okay, sir.
Yeah. Okay. So the next concept, and this is going to be an introduction to CMRR. Okay, so I am going to deal with this in detail in our upcoming class. I just want you to know as to what is CMRR in this class. Okay. We have another supporting circuit. Okay, so this is going to be an introductory concept for CMRR, okay, which is common mode rejection ratio. Now, unlike the previous circuits, okay, you can see here the previous circuit. The previous circuits used to have a feedback from the output, right? So part of the output is connected back to the transistor. But here we do not have anything as such. Okay? The output is not connected to the input. Okay. But instead what we are doing is we are connecting both of the bases together and the same voltage is given. Okay. So hence the term common mode. Okay. Common mode input. Because both of the transistors are given are shorted and it is given the same input. Right. The feedback connection from the output is absent, so there is no feedback connection here. The two input terminals are connected together and both are given 1 volt above ground level. Okay, so which means it is given about plus 1 volt. This is known as common mode input. Okay? Common mode input. There is no differential input and hence the output should be 0. Why it should be 0? Because both of the bases are shorted and it is given 1 volt. So which means the output of this differential amplifier is going to be 0 because the voltages are same, right? The voltages at both of the transistor bases are same. So what's the concept of differential amplifier? The differences are amplified, isn't it? But here 1 minus 1 is 0, so which means nothing is going to be amplified. The output is going to be 0. Since the base voltages of Q1 and Q2 are raised to 1 volt above ground, the voltage drop across emitter resistor RE is increased by 1 volt. So since both of this transistor Q1 and Q2 are increased by 1 volt, what is going to happen? The drop across RE is also increased. Why is it increased? Because the currents are increasing. If the current is increasing, then what is happening? The voltage drop will also increase. Right? But if the current is reduced, let's say instead of 1 volt, I give minus 1 volt, then the current across RE is going to be less, which means the voltage drop is also going to be less or high. What is it going to be? Less or high? It's going to be less, right? Okay. And consequently, IC1 and IC2 are increased because this current is increased. We have seen that IC1 and IC2 is divided by IE divided by 2, right? So if this increases, then IC1 and IC2 both are increased, resulting in increased drop in RC. So more current here, more drop again in RC. And this changes now. RC is connected to the base of Q3, right? So because of these changes, the output voltage is also changed because here we have RA and RB as voltage divider and the drop across RC changes. So this voltage that gets into the base of Q3 also changes. Now if this VBE changes across Q3, then what is going to happen? The output voltage is also going to change. So ultimately you should understand that whenever the input changes, okay, whenever you play around with the input, okay, then what is going to happen? The output is also affected. If you increase the input, the output is also going to get increased. We call it common mode. Why is it common mode? Because both the bases are connected together and it is given common input. This is also given 1 volt and here also it's given 1 volt, right? So any doubts, students, with the concepts we have discussed so far? Is it all clear? Yes, can I have some
Yes, sir.
responses? Fine, fine. Okay, so we have studied common mode rejection ratio, right? We have seen a problem, and I want you guys to practice this problem, right? And we have seen the input and output voltage ranges, right? And we have seen how if one current reduces, how the other current increases to compensate, and how it is impacting the output voltage. And also we have seen the types of input voltages and the basic circuitry, right? So these concepts are to be dealt with and you have to revise these concepts as much as possible. Okay,